Okay. So this is the first lecture on a introductory series in probability that we will call probability one, and we will assume that the reader is familiar with measure theory and knows basics of probability theory, like what a probability function is, what is a c.d.f, what is a p.d.f, what does how they relate, and basic definitions like that. However, we require very little knowledge of probability theory. What we'll start with today in this first lecture is the concept of independence. So two functions, sorry, so x and y are random variables. So let's not talk about random variables as of that. Sorry. Okay. So uh, suppose omega if p is a probability space, and f1 and f2 are two sigma fields such that f1 comma f2 a subset of f. Then we say these two are independent if probability of A, which belongs to F1, comma B belongs to F2. This means intersection. This notation means intersection of A and B. It is just the product. P of A belongs to F1, P of B belongs to. Intuitively, this says that knowing A and B, there is no relation, there is no overlapping between A and B. They're independent of each other. So this is what intuitively it says. So if for all A and B this holds, for all events in the sigma algebras, F1 and F2 are said to be independent sigma algebras, independent sigma fields. Just let me check once. Hopefully the microphone is off. Independent sigma fields. So this concept can be extended to random variables too. So x and y are two random variables, are two R.Vs. Then x and y are said to be independent if the corresponding sigma fields are independent. So x and y generate a sigma field are said to be independent. That is, so by R.Vs I mean maps into R measurable functions onto R Borel sigma algebra are independent if sigma x, which I define it for the first time here and probably the last time. I will use this notation for now. This x belongs to A belongs to BR. This is the pullback of the events in the Borel sigma field, and sigma y are independent sigma fields. All this notation makes sense. So these notation are not very interrelated notations. In short, two events A and B are said to be independent if, well, this thing holds for though that particular event, if said to be independent, I'm sorry, said to be independent if, well, probability A intersection B is equal to probability of A into probability of B. And one can verify that this is true if and only if the indicator functions A and indicator functions B are independent. So this may be an exercise. This is an exercise. This quickly gives some stuff that if these are independent, then if A and B are independent, so is A complement, B complement, and maybe combinations of and A and B complement and B and A complement. One can just check from the sigma algebras that this indicator function generate. Okay. So we saw one thing that so we know the notion of the smallest sigma algebra generated by a field. So if A is an event, A belongs to F, then the smallest sigma algebra generated by F is this sigma algebra. That is omega A complement phi. And from this lemma, we saw that if A and B are independent, the sigma algebra indicator A, indicator B are independent. That and f of A is this is nothing but sigma of one of A. So these are independent. So it begs us the question: if A1, okay, are certain good collection of subsets, for example, are fields. Fields by I mean under intersection they are closed, under complements closed, which trivially happens in this case, are fields, then which are independent. So a similar notion of independence may be extended to this. So like that, there is nothing about sigma fields that we require in this definition. So it must be just closed under complement under intersection to make sense. Not even that. So are fields which are subset of F, which are independent. So one can, if it does not make sense, try to formulate a definition of fields from the above definition of independent sigma of fields. Then, if A1, if AK are independent sigma fields. Um, even more is true. Even more is true. That is, there is a criteria. So, if A1, A are fields, A n comma. So this is a sequence of fields, are fields. So now we may need to make to sense what does a sequence of fields being independent mean. Are independent. So this is the definition is if any AI1, so any finite of them, any amount of finite of them we take are independent. That is any finite subset of this we take are independent fields. Then sigma A1. So this directly follows if we prove this statement. If this statement we can prove, this directly follows. Sigma An are independent. Okay. So our first task in his first lecture is to mainly prove this result, the start result. Confusion may arise that suppose sigma algebras are mutually independent. So the concept of mutually independent comes from here. So if that is if any two are independent. So is this independence extends to the whole thing? That is it enough to check any two are independent? Um, the case is not so. It happens in specific cases, surely, but in general, it is of too far weaker an assumption because that any two random variables may be independent, but in general they may not be independent. So mutual pairwise independence does not imply independence. Um, a quick example will be so x1, x2, x3 are Bernoulli half random variables. So these are identically distributed and Bernoulli half, these are IID. So by this notation, I mean they are identically distributed because they are Bernoulli half and they are independent random variables. A question does arise: does this random variables indeed exist? And we will show later that it does exist, but assume for now. Then A1 is the event x1 equal to x2. Sorry, this is x2 equal to x3. A2 is the event x1 equal to x3, and A3 is the event x1 equal to x2. So since we have started with independent random variables, P of A1 intersection AJ is nothing but probability x1 equal to x2 equal to x3. Just check this. This is indeed that. And this is probability x1 equal to x2 equal to x3 equal to 0. So not like this. The writing is sloppy here. This is x1 equal to 0, x2 equal to 0, x3 equal to 0, plus the event x1 equal to 1, x2 equal to 1, x3 equal to 1. Now, this is 1 by 8, this is 1 by 8. So we get this is 1 by 4 because Bernoulli half. So Bernoulli half means probability xy equal to 0 equal to probability xi equal to 1 equal to half. Sorry. But, and one can check that P of A1, AI is equal to 1 by 2 for each I. But, so P of A1 intersection A2 intersection A3 is same as this P of x1 equal to x2 equal to x3, which is 1 by 4. So which is not equal to product of P of A1, P of A2 and P of A3. So these events are mutually independent, but not overall independent. That is, so in random variables A1, A2, A3, sorry, integrated A1, A3 are mutually independent, but not independent. So we necessarily these random variables. This is a discrete. So a discrete random variable means uh, necessarily whose support is countable. So support is finite here. One try to find examples, and an exercise will be try to find examples of continuous random variables. Try to find examples for continuous random variables. By continuous random variables, I mean it has a density. You can assume a continuous density. There are certainly there are certainly uh, uh, exercises that there are certainly random variables such that which are continuous R.Vs, but they are not which are mutually independent, but not independent overall. Okay. Now, in order to prove this, we need a very important lemma from measure theory. That is the monotone class theorem, the start result monotone class theorem. It says if so a monotone class, so M is a monotone class which is a subset of P of sub omega. If it is closed under increasing and decreasing limits, that is, if a n increases to a, that is, it has omega and phi, and if a n increases to a or a n decreases to a, then if a n is in M, then a is also in M. Okay, so if so, the sense our smallest monotone class also makes sense by similarly as of smallest sigma algebras and smallest the intersection of monotone classes in a monotone class. So if A is an algebra, my notation may be a little sloppy here and there, but do pay mind to it. It helps as an algebra. Then M of A is equal to F of A. That is the smallest monotone class generated by A that obviously contains F of A that is exactly equal to F of A, because one can check that F of A is also a monotone class. So using that theorem, we prove the main theorem for today, which is the start result, which I write again. If A1, A are algebras, are independent algebras, then sigma A1, sigma n are independent sigma algebras. This result has many implications, which we will certainly see later. So the proof goes like this. So we'll show actually M of A1. So not this actually. So first we will show sigma A1, comma A2, comma AN are independent. So since then we will iterate taking this as the sigma A1 as the new A1, which is a sigma algebra, so it's definitely an algebra, and then change it to A2 so that then A3 like that on. So proving this is enough. This is enough to prove. So let us consider set G to be all such C belongs to sigma A1 such that a probability of C intersection B2 intersection Bn equal to probability C into probability B1. That is, these are independent. This holds for all C belongs to sigma. For all B1, sorry, all B1 up to Bn, for all Bi belonging to Ai. So an exercise is, so if, so what will show that G is a monotone class? So if G is a monotone class, first notice G contains A1 by the by a hypothesis. And if G is a monotone class, G contains M of A1, which is equal to sigma of A1, and we are done. So it's enough to prove that G is a monotone class. So how will we prove that? Uh, Suppose Cn increases to C. So we need to show C's in this stuff. So if here increases to C, then Cn B2 intersection Bn increases to C intersection B2 intersection Bn. Use continuity from above. So that's just a technique. Use continuity from. And similarly, there use continuity from below. Since probability measure, you can do all this freely. So we are done. So we have actually proved our important lemma. So now, a very important condition of when random variables are independent. So when we need some condition, when are x1, xn independent? So the result is if and only if the c.d.fs. So the joint c.d.f is the product of the c.d.fs. So recall the joint c.d.f of this of f of x1 fn. Let us call this f. F of t1 comma tn. Let us call this if it is this is x equal to probability x1 less than equal to t1, xn less than equal to tn. And if independent, we will, if suppose x1, xn are independent, we will require this is product of fxi t1. So the CDF is the product of the joint CDFs. The joint CDF is the product of the marginal CDFs that we know. So, so this is a necessary condition. We say that this is also sufficient. And the proof follows is so the proof. So what we have necessarily shown is that what we have necessarily shown is that probability. So if we consider these events, AI equal to x belongs to xi belongs to minus infinity comma ti t, where t belongs to r. Not this. Yeah, t belongs to r. We have shown that AIs are independent. There is a catch here. AIs are not algebras. This suddenly generate the whole Borel sigma algebra, but AIs are not algebras. They're not even semi-algebra. That is, AIs are not fields. Sorry, that is the notation we are using. AIs are not fields. So fields, algebras, they are used. So in probability sense, more fields, the notation terminology fields is used. So AIs are not fields, but the thing is they're closed under intersection, but they are not closed under complements. So we have to tweak this a bit. That is, we have to show that if AI is, if we define A star I as xi belonging to A comma B, T belonging to, so A, the notation, the standard notation, minus infinity less than equal to A less than B less than equal to B less than equal to infinity, then E star I is independent. So the proof follows like this. Let me just give the idea of the proof. If so, um, so actually, this is something called a pi system, and that is it is this is closed under intersection, but not on the complements. But AI can be extended to a semi-algebra. So, so first, the first step is to show that AI bar, which is xi belonging to either elements of the form minus infinity comma t or t comma infinity. The notation is like this: t belongs to R. This is this thing is these AI bar are independent. This is not difficult. This is actually follows directly from that statement that if A and B are independent, complements are also independent. In the complement combinations are also independent. Then show that if AI double bar is defined as all finite intersections of A case, B case, sorry, from 1 to n, where BK belongs to AI bar, this then AI bars are also independent. Also, this is also simple to show that this holds, and this will be a semi-algebra, semi-field, or whatever notion you like, and then extend it to algebra, and then extend it to the sigma algebra. So somebody who is familiar, that is why the measure theory concept is necessary. So this actually proves this result that then we use this theorem. So if so, this actually says the theorem actually says a collection of random variables are independent if and only if the joint CDF is equal is the product of the marginal CDF. So if x1 and xn are continuous CDFs, that is they have a density. So if x1 and xn are continuous CDFs, so the previous theorem continuous independent CDFs. So the previous theorem says that if this is equal to x, this push forward push forward measure is nothing but the product measure p x1 inverse product p x1 inverse. So this is just that measure, the product measure. The previous theorem says exactly that the this push forward measure is nothing but the product measure. Then, if they have densities fi, then joint density of x is fi of product fi xi. So this is the idea, and this is also a sufficient condition that if the joint density of x is product of the marginal c.d.fs, so then it is independent. That follows from this theorem. One has to work a bit, but one can show that this happens. Yeah. Now, to end the first discussion on this, we will prove an important result, that is lemma. So suppose there is an array of independent sigma algebras. That is, suppose f1 comma 1 comma f m1 comma 1. For every this, then there is f1 comma 2. There is f, so kind of an array, if m2 comma 2 and so on. There is an array of sigma algebras such that these are independent. So I am not saying these are independent, I am saying these are independent. Okay. Then, okay, let me think a bit. What is the exact question I want to formulate? So actually not. The question is everything is independent. That was it. So this array, this entire collection of array, which is a countable collection, are independent R.Vs. R.Vs. Then are independent sigma fields. So just saying that these are independent is not enough. Then, if I define Gi as sigma union, the smallest sigma algebra generated by F, so everything lies between the ambient space omega F comma P, I comma J, with the runs between J. Then Gi are independent. So an easy proof of this follows from the fact that if I define A to be sets of the form Aij, sorry, let's call this A. So we take for fixed type, define. So did I define pi system earlier? Yeah. So this is a pi system, and actually this lemma says that. So this lemma we started with a pi system, and the generated sigma algebra was also independent. So this theorem can be improved. We need something called the Daikin pi lambda theorem for that, which is actually a consequence of the monotone class theorem. So instead of this, if we assume that this is a pi system, the result still held. What I mean to say, and that follows from something which is a consequence of the monotone class theorem. One can see any standard book, Duret, Billingsley for a proof of that. So for a fixed I, we define AI to be all elements of the form Bij, intersection of the form, where Bij comes from Fij. So this is a finite intersections. So one can see easily this is a pi system. If Ij is contained in AI for all j, for all j. So this thing actually, yeah. So and from there, since that, and AI are, so for each I, and due to the consequence that these are all independent sigma fields, AI, which are pi systems, are independent. So from the theorem that we prove, now the Daikin consequence is that GIs are independent. So GIs are independent by theorem. Okay. So let's say a corollary of this, and which is probably a very important result. If xi xn are independent random variables, a sequence of independent R.Vs, and suppose we group these xi's. Suppose x1 to xn1 is a group, xn1 plus 1 to xn2 is a group, and so on. So this is our f1, this is our fn1, this is our f. So this is our f11, fn11. This is our f12, fn. Let's call this m1, fm22. So like this. Let fi be Borel measurable functions from R m1. So the size of this is m1, R my to R are Borel measurable. Then fi x1 to, so let us call this x, the notation used, x ni minus 1 plus 1 to x ni are independent for all I. This is a direct consequence of the previous theorem. So this random variables will be in GI, and from there it follows. So actually, a better notation would have been, this is nothing but the smallest sigma algebra containing, this thing is the smallest sigma algebra containing Fij's. So this is what I mean to say, the smallest sigma algebra containing all Fij's. And this sigma algebra will be contained in these GIJs in this case. So consequence of this is, if x1, x2, x3, x4 were are independent, so is x1 plus x2 and x3 plus x4. These are also independent. if x1, x2 is a sequence of independent random variables, then x1 and summation x2, provided hopefully it makes sense, provided it makes sense, are independent R.Vs. So we can freely manipulate random variables to our advantage. Okay. Now there is a concept that there is a degree, there is a numerical value which you can associate how some sense associate to how independent to random variables are. It's not a perfect uh, numerical coefficient, but it does imply that is we have something called correlation x comma y, which is defined as expectation xy minus expectation x expectation y divided by we assume that these random variables are non-degenerate. X and y are non-degenerate random variables, that is not constant, and non-degenerate random variables. Then variance of x root, variance of y root. So this is what is called correlation, and one can show that this modulus is less than equal to 1. And if x and y are independent, and correlation xy equal to 0, then correlation xy equal to 0. The converse is necessarily not true, that correlation xy is 0. So this stuff in general is said to be uncorrelated, uncorrelatedness. So two random variables are said to be uncorrelated R.Vs if the correlation coefficient is 0. So suppose x and x square. So suppose x follows normal standard normal. X follows standard normal. Then x square follows something called chi-square distribution, but we don't need that. So x and x square. So an exercise is show that x and x square are not x and x square are not independent random variables. It can be shown easily. If that happened, some very problematic situations would arise. Intuitively, one can understand. Intuitively, one can understand there's a definition. So this is an exercise. Check this are not random variables, are not independent random variables. So x dot x square expectation. So two random variables are said to be uncorrelated if e of xy equal to expectation x into expectation y. So one can see x and x square are uncorrelated because this is 0 and this is x cube, and by the odd functionness of the integral, this is also 0. However, they are not independent. Okay. So let me keep it here because from the next lecture I will start here. It will look nice. So ex cube equal to ex into x square. So uncorrelated does not imply independence, but uncorrelated independence imply uncorrelatedness. And uncorrelated is some sort of a very crude generalization of independence because like independence, so they are also stable under linear transformation. That is, I mean to say, if x and y are independent, so is ax plus b and cy plus d. Same is true for uncorrelatedness. In fact, the correlation coefficient does not change. Does not change. So this was for the first lecture.